Good morning. So let's start our lecture now. Chapter 3, Parameter Estimation. So in this topic, we try to estimate the parameter or to find the parameters. So in risk theory, the parameters are given, right? But now we have to find the parameters. So in chapter 1, our topic is talk about the complete data. Chapter 2 is incomplete data. And now, if I give you the data, so we have to find the parameters, whether it's a Pareto, exponential, or whatever. Okay, so we have to find it. We have two methods, class. The first method is using method of moments. Okay, here we go.
Chapter 3, Parameter Estimation. In this section, we want to estimate parameters in a parametric model by using finite random samples taken from the underlying distribution. We will look at two methods of estimation, that is, the method of moments and the method of percentile matching. 3.1 Method of moments. Let x be a random variable with parameters data1, data2, and until data m. So we have altogether m parameters. For example, for a Pareto distribution with parameters alpha and theta, so where this alpha we can name as data1, and this data we may name as data2. And so on. We assume that all n observations are from the same parametric distribution x, that is, this random variable x has n observations, that is x1, x2, x3 until xn. In particular, let the distribution function is given by this df of x given the parameter data, and this data transpose which is equals to this m parameters, where data t is the transpose of data, where data is a column vector containing the m parameters to be estimated. That is, this data is a column vector. That is, we have data1, data2 until data m. We will also denote the k raw moment of x by this notation, that is the mu k prime in terms of data, which is equal to the expected of the x to the power k given the parameter data. And this we have studied in risk theory chapter 1. For a sample of n independent observation of this data, and from this distribution we let the estimate of mu k prime be the empirical estimate of the k moment, where mu k prime, which is equals to the summation of x to the power k divided by n. A method of moment estimate of the vector data is any solution to the following system of m equations. It means that at the vector of the parameter data, then this is whole, where this is equals to the summation of the xi to the power k from 1 to n, which is divided by n, is fulfilled for the distribution of x. So please take note, the mu1 prime is always equals to mu when the k is 1.
Okay, class. Here, we talk about the method of moment. So that means we have to involve the k moment. That is this formula. Okay, so usually we will involve the first roll moment and also the second roll moment. Okay, so because from here we can calculate the mean or maybe variance, okay, by using the first roll moment and also the second roll moment. So we will apply this formula later, okay, to compute the parameters. Okay, so let's carry on to next slide. So we go to example 1 now.
Example 1. Let x be a random variable of the independent observation of this n data such that x is normal distributed with the parameters of mu and sigma square. Use the method of moment to prove that these two equations hold. Solution for example 1. From the independent observation of this n theta, that is from x1 to xn, of the random variable x, where x is normal distributed with this parameter mu and sigma square. Since mu and sigma square are the respective mean and variance of this random variable x, then for the sample moments, we have the following. We have the first roll moment, which is equals to the summation of xi, where the I is from 1 to n and divided by n. Now, since the expected value of this random variable x of normal distribution, which is equals to the estimate of mu. So therefore, this estimated mu will be equal to this result. That is so we prove the result. Next, we go to second roll moment. For second roll moment, we will have this expected of x squared will be equal to the summation of xi squared, where I is from 1 to n, and this result divided by n. Since the variance of this random variable x, which is normal distributed, and this is equals to the second roll moment minus the first roll moment square. Therefore, this variance is the estimated of this sigma square, and which is equals to the second roll moment result from this sample moments. So we will have the summation of xi squared, where the I takes from 1 to n, and divided by n minus this result we have found in the first roll moment, that is the summation of xi, where I takes from 1 to n and divided by n squared. So we prove the result.
Okay, so these two formula means what? It means that if x is normally distributed with the parameters mu and sigma, so how we want to find the value? Okay, so how we want to find the value of these parameters mu and sigma? So if I give you the parameters, okay, if I give you the observation, okay, so let's say you have one set of data, okay, and we know that this data is follow the normal distribution. So how can I calculate these parameters? So I use this formula. So I sum up all the data divided by n. That will be the average, that is mu. Okay, for normal distributed. So for normal distribution, let's say for sigma, then in order to calculate the sigma, then I have to use this formula because I can sum up all the mean, okay, sum up all the data to get the means after square, and then after that we can sum up all the observation square. Okay, so from here, from this result, we can get this sigma square. Then you take a square roots, you will get the value of the sigma. So this is a way we use a first row moment or second row moment to calculate the parameters. So for this example, it's just want to show you that this is a formula to calculate the normal distribution. Okay, so let me show you another slide. So this topic actually quite easy. So we go to example 2 now.
Example 2. Use the method of moment to estimate parameters for the exponential, Pareto, and gamma distribution for the following data. So that means we try to estimate the parameters for exponential, this data, and for Pareto, we try to estimate the parameters alpha and theta. And for gamma distribution, we try to estimate the parameters alpha and theta. Here we go. Solution for example 2. Let x be the random variable of the given data. Then from the sample moment, we have the following. For the first row moment, we can estimate this random variable x, which is we sum up all the data from 27 plus 82 plus until the last observation, that is 15743, and this total divided by the sample size, that is 20, and we will have 1424.4. Next, we go to second row moment. We have this second row moment, which is equals to, we sum up, that is 27 square plus 82 square plus until 15743 square, and this total divided by 20, and we have 13,238,441.9. So now we can go to part A. So let x is exponential distributed with the parameter theta. Now since the expected of this random variable x, which is theta, therefore we can estimate this parameter, which is equals to this value, that is 1424.4.
Okay, clear, right? So for exponential distribution, because the expected of the x under this exponential distribution is theta, so that means the theta straight away you can get from this average that is here, 1424.4. Okay, so exponential very easy. Let's go to part B.
Part B. Now assume x is Pareto distributed with the parameters alpha and theta. Now from table C, we know that since the first row moment, which is equals to theta over alpha minus 1, and the second row moment, which is equals to 2 theta square divided by alpha minus 1 and alpha minus 2. So therefore, this result which is equals to 1424. Therefore, this theta divided by alpha minus 1 is equals to 1424.4. Say this is equation 1. And for the second row moment here, that this will be equals to this figure. So we will have 2 theta square divided by alpha minus 1 and divided by alpha minus 2, which is equals to 13238.441.9. So we name this as the second equation. So we try to solve these two equations. Then we will get the parameters value that we estimate this alpha, which is 2.442, and the estimate value for this theta is 2053.985.
Okay, now for part B here, we have to invoke the second row moment. Okay, so this formula you can get from table C, right? This the first row moment, second row moment, you can get from table C, and this value is our calculation value. Okay, and if you want to solve these two equations, I believe I didn't show the detail working. I believe you know how to solve it. You just divide the first divide by 2, theta and alpha minus 1 gone. Or in other words, you just substitute theta alpha minus 1 here. So you will have theta and alpha minus 2. So you solve again the new equation together with 1. Okay, you will have the result. You practice yourself. It's quite easier to solve this simultaneous equation. You need to divide, or you substitute the whole thing. Substitute theta divided by alpha minus 1 inside here, because this is 2 theta square, which is equal to theta divided by alpha minus 1. So you can substitute direct the whole thing. After that, you can solve again. Okay, so this is part B. This is the way how we calculate the parameters of Pareto. Okay, so you have to involve the first row moment and also the second row moment. Remember, you will have the formula from table C compared to the value that we have calculated. Okay, let's go to part C.
Now we go to part C. Assume X is gamma distributed with the parameters alpha and theta. And from table C, we know that the first row moment of this gamma distribution, which is equals to alpha theta, and the second row moment, which is equals to alpha times alpha plus 1 and times theta square. So again, this result, which is equals to 1424.4, and this result second row moment will be equal to this. And so we will have alpha theta, which is equals to 1424.4, and this result from the second row moment, that is alpha times alpha plus 1 times theta square, will be equal to 13238.441.9. So we name this as the first equation, and this is the second equation. So again, we solve these two equations. Then we will have the estimated parameters, that is estimate of alpha, which is equal to 0.181, and the estimate of theta, which is equals to 7869.61.
Okay, so again, here is the same, that you can substitute the whole thing alpha theta inside here, because this is alpha times theta square, right? So you can take out one theta together with alpha. So substitute the whole thing inside here, then you left alpha plus 1 multiply data. Then again, you can simplify again with this equation 1. Okay, you have to solve the simultaneous equation 2 times, like Pareto. So you will have the answer. So I believe the solving simultaneous equation, you should know how to handle it. Okay, it's quite elementary. Okay, so this is example 2. Let's go to example 3. Here we go, example 3.
Example 3. For a sample of dental claims, that is x1, x2 until xn, you are given the following: that the summation of x is given by this value, and the summation of x squared is given by another value. Second, claims are assumed to follow a log normal distribution with parameters mu and sigma, where these parameters are estimated using the method of moments. Calculate the limited expected of x kept at 500 and the mode of the fitted distributions. So we need to use the method of moments to calculate the values of mu and also the value of sigma. So once you have these parameters value, then we can solve this problem by taking the formula from table C when substitute these values of parameters mu and sigma. Solution for example 3. Let x be the claimed random variable such that x is log normal distributed with this parameter mu and sigma. Then from the sample moment, we have the following. For the first row moment, we have the expected of x, which is a summation of xi, where the I take from 1 to 10 because we have 10 samples, and divided by n, where your n is 10. So this summation is given by the questions, that is 3860, and divided by 10, we will have 386. Next, we go to the second row moment. So from the second row moment, we will have the expected value of this x square, which is given by the summation of this xi square, where the I takes from 1 to 10, and the whole result divided by 10. So again, this value of the summation of x squared is given by the question, that is 4574802, and divided by 10. So we will have 457,480.2. But from table C, we have the expected value of x, which is equals to the exponential to the power of mu plus 0.5 sigma squared. And the second row moment, from table C again, we will have the exponential to the power of 2 mu plus 0.5 sigma squared. So obviously, this will be equal to this. Therefore, the exponential to the power of mu plus 0.5 sigma squared is equals to 386. So I name this is equation 1. And the second row moment, this result, which is equals to this. Then I will have e to the power of 2 mu plus 0.5 sigma square, which is equals to this result, that is 457,480.2. So I name this is a second equation. And now we try to solve equation 1 and 2, then we can estimate the parameters of mu, which is equals to 5.3949, and the estimate of this sigma square, which is equals to 1.1218.
Okay, class, again, I assume that you know how to solve this simultaneous equation. Yeah, you can take log both sides, okay? You can take log both sides, then you solve the mu and the sigma square. Or you can straight away expand this, because this is a mu e to the power of mu times e to the power of 0.5 sigma square, right? Here also the same, that this is a e to the power of 2 mu times e to the power of 0.5 times sigma square. Then from here you divide, you also can solve this simultaneous equation. There's many methods to solve it, class, up to you. Okay, so I believe you know how to handle it. For those who are not sure, you please practice. Okay, in fact, all these are Form 4, Form 5 method, how to solve this type of simultaneous equation. Okay, so we found the parameters mu and sigma now. Okay, and now we can go further for this question.
Have this parameters, and now we can calculate the limited expected value of this random variable 500. So from table C, we will get the formula, which is equals to the exponential to the power of the mu 5.3949 and minus 0.5 times the sigma square, that is 1.1218, and multiply the CDF at log 500 and minus the mu 5.3949 and minus the sigma square 1.1218, and divided by the sigma, that is become square root of 1.1218, and plus the 500, that is the x value, and multiply 1 minus of this CDF at log 500 minus 5.3949 and divided by the sigma, that is the square root of 1.1218. So we try to simplify this. We will have exponential to the power of 5.3949 and multiply the CDF at negative 0.2852 and plus 500 multiply this result, which is 1 minus CDF at 0.7739. So if we do further calculation, we have the result, which is 259.4. Next, we can calculate the mode of this log normal distribution. And again, from the table C, that this is equals to exponential to the mu minus sigma square. So by substituting the value we have found just now, that this is equals to exponential to the power of 5.3949 minus the sigma square, that is 1.1218, and we will have 71.7437.